Now, the next one actually is not mine. It comes from our good friend and colleague, Carlos Rebello. Carlos unfortunately could not make it today, but he gave us this really nice presentation, and he's the man who took care of transforming, let's say, Eurocode 8 part 6 into a part of Eurocode 8 part 4, is essentially what Christoph Butenweg said earlier. So, coming from Carlos Rebello, towers, masts, and chimneys, with me as the conduit. Just an overview, scope of application, the basic structure of the standard, some main changes and simplifications that had to happen compared to the older standard, and then a brief introduction and discussion of the relevant rules. In general, this is part chapter 10 or closed 10, if you will. You can use it to design tall, slender steel towers, guide masts, and chimneys. And of course, you cannot do it on its own. You have to use Eurocode 3, part 3, and the relevant parts from the steel design, essentially, and concrete design. Chapter 10, the part 10, it does not completely cover the design of structures for electrical power transmission. It does not cover, because these are often wind load designs, okay, they're not concrete, they're not heavy structures, so seismic design is not as important. In general, there is issues of ice loads, unbalanced wire loads, so only tangent towers, meaning the towers that have vertical cables hanging from them, are the ones that you look at. The ones that are supposed to take the wind loading, so-called angle or dead-end towers, look to other standards. You should not apply this to cooling towers and offshore structures. And towers supporting tanks, of course, you should look at what was discussed earlier by Roberto and Christoph. Other Eurocode standards, EN standards that are applicable, for example, 13084 for freestanding chimneys, 13084-7 for freestanding chimneys as well, product specifications, etc. This is concrete, this is steel. Base of design, discuss the basic rules for mass stiffness modeling and, of course, the behavior factors, definition of limit states, damage limitation, fully operational discussion. And of course, then we go to some specific rules for reinforced concrete chimneys, which are needed to achieve a ductility behavior factor of 1.3, some rules for steel chimneys to get the proper QD that you need. And again, for steel towers with a limitation of 1.3 for truss tubular towers. Again, these are just rules of how you should design to make sure, or let's say dimension and size, to make sure you achieve what you need. Now, basic changes, of course, new structures and different, it was a major overhauling, let's put it this way. But quite important from the older standard, if you're a fan of rotational spectra, I'm really sorry this is gone. The reason being that rotational spectra was employed in the code. There was a lot of work and annexes through that, but in reality, rotational spectra as an input motion, it doesn't exist in Eurocode 8 part 1.1, so it didn't make any sense to have this there. We just had to remove it. There are also issues of decreasing the behavior factors, especially those used for the design of concrete chimneys. And in this, we've gone closer to the CI/CIND codes and their discussions, and also recent findings by Wilson, who did inelastic response analysis of reinforced concrete chimneys, heights ranging from 115 meters to 301 meters, pretty high ones. And they recommended a Q of about 2 as a maximum. So essentially, you will see there is a Q of 1.95 here. Now, in general, the model should include some modeling requirements, rotational, translational stiffness of the foundation, cables and guys. Of course, sufficient degrees of freedom to determine the response of any significant structural element, equipment, or appendage. Refer to the previous discussion about ancillary elements. Some of them are pretty large, like big antennas. You have to include them, okay? Relative displacement or the supports of the equipment or machinery that may be attached to this, any piping interaction, externally applied structural restraints, hydrodynamic loads. And quite important, there is a rigid diaphragm assumption that we often like to use, but if that has to be used, please make sure that you apply a horizontal bracing system for steel towers or stiffening rings, okay? If it doesn't work, I'm afraid you have to do three-dimensional dynamic analysis to work out all that stuff. Now, some general ideas about the behavior factors. Maximum value of the behavior factor is calculated using 1 for the overstrength part, 1.5 the material part, if I remember well, and QD is the ductility part, which will be defined respectively for RC chimneys, steel towers. Now there is a bunch of reductions that you need to account for due to irregularities. And in this case, there is a modification factor of KR, okay, which has to be used to reduce the overall behavior factor of the structure. And here's an example for reducing according to existing irregularities. Reduction factors can go from 0.8 down to 0.7 in some cases. Limit state verification, the classic one, of course, is significant damage as the limit state. You need, of course, to have the proper capacity, and you design for behavior factor using a value of Q greater than 1.5, going to DC2, for example. If you decide for low dissipative factor, of course, Q has to be equal to 1.5, maybe less. 1.5 is the standard. Guide masts, we do not believe they can be done in elastic in a very reliable way, so best go with option B, DC1. Second order effects need to be applied, of course, and if you have delta stability coefficient factor, essentially added moment at the base divided by the first order overturning moment, it should be less than 0.1 to disregard P delta. If it's more than that, you should do something about it. Typical stuff, nothing new. Now, steel connections, obviously, if they are non-dissipative, use Eurocode 3. If they're dissipative, please go to Eurocode 8.1.2. Easy. Stability issues, you have to use the equivalent, the relevant rules of Eurocode 2 and Eurocode 3, of course. And you may use class 4 sections subject to a number. This is called for, let's say, very slender sections, okay? Steel ones. And be sure that you limit, for example, to ductility class 1. You apply relevant rules from Eurocode 3.1.1, of course, and make sure you limit the slenderness in the link members, especially because they are prone to buckling, and in primary bracing members, because those buckle as well, although not as catastrophic as the leg members. Now, for the damage limitation, in general, you want to reduce or actually remove, if possible, unacceptable damage to the structure and its ancillary elements. And you need to use specific criteria, which may be imposed by the usage of the structure itself and also by the client. But as a basic default criteria, essentially you work with, if you will, the roof drift. Roof drift should not exceed 0.5% for towers and masts. For chimneys, if you're talking about a waste gas flue, that's again a 0.5%. If you're discussing the liner, and the liner, remember, for a chimney, it's quite important, it's what protects it. Essentially, the slightly more relaxed requirements in some cases, you're allowed to go to 1.2% drift in general, or up to 2% if your liner is designed, okay, if it's designed to accommodate some displacement. Now, in general, fully operational is something we cannot tackle easily because it depends on the specific requirements of the project. So there's a nod to that by saying that you should account for this and make sure that you take care of it when needed, but no default criteria is available. Design for dissipative behavior for reinforced concrete chimneys in general, minimum concrete class is C2025. QD, your ductility factor, ductility-based behavior factor component should be less than 1.3, and you should take care of the critical region. Critical region is the part essentially at the base of the chimney, defined over here, up to a height of D, meaning a diameter above the base, and any abrupt change of section from one level to another or any opening, you should call it a critical section. You should be careful with it. In general, there's a bunch of minima that you need to make sure of, for example, no horizontal construction joints, ratio of outer diameter to wall thickness, which should not exceed 20. Essentially, you need to make your structure robust enough. So whenever there is a change in the homogeneity and uniformity along the height, and there is a criticality there, and of course at the base, because that's where you get expected trouble, you should make sure that this is adequately protected. Now, some, again, for reinforced caulking chimneys, dissipative behavior, some minimum reinforcement issues. If you're looking at large diameter values, meaning D greater than 4 meters, vertical and horizontal reinforcement should be placed in 2 layers, okay, one internal, one external, and there is a minimum ratio for the horizontal reinforcement in the cross-sectional area. If you're talking about lower diameter chimneys or part of a chimney, if you will, you can place vertical and horizontal reinforcement in 1 layer. You don't need to have external, internal, just 1 layer, if you will. And again, you have a less stringent actually a more stringent requirement on the reinforcement in each direction in the section. Now, spacing of reinforcements, you should not have a spacing of more than 250 millimeters for the vertical bars, and for the horizontals, no more than 200 millimeters. And if you have an outer and an inner layer of reinforcement, you have to have cross ties, at least with a spacing of 600 millimeters, both vertically and horizontally. And the classic one, if you have openings, okay, in the chimney, which is actually quite typical, at the base especially, you should reinforce them, or the border of those openings. And the idea is that the area of the additional horizontal and vertical reinforcement in each direction, vertical and horizontal, should not be less than that of the bars which you removed, which were discontinued by the opening. Sometimes it may need to be more. Vertical reinforcement ratio should be at least 7.5 per 1,000. Again, for steel chimneys now, with hollow circular cross-section, dissipative behavior. If you're looking at guide steel chimneys or very typical steel chimneys, because they're quite light, seismic loads are usually not governing the design. There are cases, for example, combined cycle power plant chimneys with very large diameter, like 8 meters, or very sizable openings. We're talking about 25-meter high openings in some cases. In moderate to high seismicity areas, in those specific situations, you may have an issue of seismic loads governing the design of the chimney. Unfortunately, it's not recommended that you use DC2 or more, because it's very difficult to have in such slender sections a plastic hinge safely developing at the base of the chimneys or wherever this opening is. Typically, local buckling will happen first, so typically provide support, design non-dissipatively, or you may use dissipative behavior in many cases with a steel frame or truss structure in general to provide lateral support. That's another discussion. Now, for steel towers, again, this depends a lot on the system that you're using. You might have moment resisting frames, eccentric brace frames. You might have constructing brace frames. In both of those cases, you should look to Eurocode 812 and how they do the design for dissipative behavior, because they know best. If you have a rigid diaphragm, it should be capable of assuring the rigidness that you need, and make sure that this is actually provided if you use a high Q value, meaning a value higher or equal to 3.5. In those cases, here's an example of potential bracing patterns that can give you such a rigid diaphragm, assuming they're sized, of course, properly for a steel tower. Design for dissipative behavior, again, it depends a lot, of course, on the bracing pattern along the height of the tower. Here you're seeing some examples of what is classified as a K bracing pattern. Remember, K bracing patterns are not really desirable. Doesn't mean you cannot use them, but it's the classic situation of if one of these buckles, there is no support at the node, meaning that the leg can buckle very quickly. So in those cases, DC1 and behavior factor 1.5. If you have V bracing or X bracing, this is V bracing, by the way, you can go to rules of Eurocode 812 and work from there. This is another case of concentric braced towers. Again, go back to the relevant parts of Eurocode 812, or you may have X-braced ones. And of course, as you can tell, you can get pretty good behavior factors in these cases. And this is it.
Thank you, Dimitrios, for this very interesting presentation full of important details. So there are some questions. Yes. Let me read the first one. It's from Carlos Arboleda of SDA Engineering. So the amplification factor AMP for component acceleration, PCA, compared to the floor acceleration, so PCA or divided by PFA of ground acceleration, as stated in the NIST GCR 1819-1743, the recommendation for improved seismic performance fall within the range of 2 to 8, depending on the complexity of the structure. In case of the simplified method 3 adopted by Eurocode, you explain it very well, this is between 1.3 to 3.4, which lacks detailed knowledge about the dynamic characteristic involved. How do these ranges compare?
They don't necessarily. NIST part was not, the idea over there was they did not care that much about the certified component, if you will. The discussion of the fuse was included, but not necessarily perfectly as a certified component, if I remember well. So they opted for more conservative factors, meaning that the engineer, a designer could use, for example, an angle section to support a component, and let's say work on his own in some cases. It was a recommendation. Now the higher range, so that's maybe takes care a little bit of the lower range. The higher range, which pertains more to method 2, the simplified approach, where you know nothing of the structure theoretically, there they go higher. They go to 8. We go to 7, actually 707. Yeah, just 7. This is actually the maximum that was employed by Eurocode 1. Eurocode 8-1, -2. So we didn't want to go higher than that. We could have gone higher. This is why you saw some exceedances in some cases. But let's say that there was a long discussion even in NIST. I was actually part of that team when they were developing it. And there was a long would you like to broaden the peak and lower the amplification? Or would you like to keep it very narrow and keep the amplification high? It's a choice. It's really a choice. And there's no perfect answer about it without some shake table testing, to be honest. So it very, very much depends on details. You get slippage, then you assume that you can take down the plateau a bit. Do you not? And everything is perfectly tightened and fantastic. The only thing that really saves us, to be honest, in the end, and we're allowed to go to 7 or even lower, actually, if we wanted, is that tuning is a very, very sensitive thing. It's like a little violin, and then you have to get the perfect thing to get that perfect notes. Anything goes a little bit off, it kind of ruins it and lowers the amplification factor. So we're kind of banking onto that.
Yeah, thank you. I totally agree with you. It's not an easy task. No, I don't think I don't see any other questions. I have a couple of questions for you, just to conclude the story. So that comes from my experience in working on industrial plants. So, what about the interaction between ancillary elements? So, for example, pipe, flasks, tanks, on several floors. So there are some suggestions how to account for, in a simplified way, these, in my opinion, crucial aspect, because sometimes the response, local response can change dramatically. If you do nonlinear or maybe in any case time history analysis, you can discover very big surprises. So I don't know.
Oh yes, true. Oh yes, it's true. And the more, let's say, elastic your components are, and the less elastic your structure is, and the heavier those components are, the more important this becomes. And actually, there is no rules to tell you. There are some recommendations that say people say, seen it in American code, say 25% of the max mass of the structure is allowable for a component to be interacting, which is actually quite a lot. There's lots of discussions. There are lots of discussions really, and there is no good answer right now. There's no good answer. So we opted to stay away from that and just say conservatively, if you start seeing interactions, don't use simplified approaches. Try to use something better. Having said that, I feel that a fuse, this method 3 with a fuse and elasticity included, can help quite a bit with that matter because it just ruins your interaction in many ways.
No, in fact, this is my experience. The trend, especially for the owners of the plants that are very sensible to money, is to use advanced nonlinear analysis, because in this way they can save money and they are more happy like this. So they have more effort at the beginning, but to save.
I'm a big fan of improved methods of analysis. As long as you can do it and you've tested yourself, do it. I agree.
Okay, last question. I don't know if there are some in the meantime, some other questions. No, I don't see. So in the chimneys, I don't know that is in your matter, but just to maybe you know, it is crucial. The rule are also there on non-structural components. For example, there are some refractory material inside that can be damaged, and this is during the operation that can continue just after the earthquake, can induce a local damage and a very big problem inside. But I have not seen indications on the new version. So
it's true. There is only something on the liner. For the liner, yes, we included some deformation limits, but nothing beyond that. Yes.
Because this is, of course, is always a non-structural aspect that sometimes is neglected, but in this case, maybe should be taken into account. Okay, so thank you, Dimitrios. I would like to close this webinar, thanking you all for the intense participation that animated the webinar with a big surprise to me. Let me also thank once again Rita Bento for the organization, the effort. Christoph Gutenberg, of course, as a coordinator of this webinar. Also Marco Marinkovic as a co-chair of this webinar, and all the speakers, of course, who have provided a very clear overview on the novelties and of this new generation that will last for other 20 years. So we will have all the time to apply this. I would like to leave the word to Rita for the closing this webinar, and thank you once again.